do this last one. Actually, you know what? Let's skip ahead. I want to do an overlap one. Let's do the area inside of a loop. Here's a lemniscate because we haven't dealt with one of those yet. If you go ahead and graph this in your calculator, you'll find out it's actually it takes a long time to get the whole thing to graph properly. If you put it in there, I would it's tough to find a domain that matches this to see what happens, but that's the lemniscate that goes with it. The lengths, of course, maximize at 4 and -4. Now, to get some of those points, we'll just do a quick table so you can just get an idea of how it works out. If you put in 0, of course, you get cosine of 0, which is 1. 4 times 1 is 4. But remember, we're solving for r, so we have to actually think of there's the square root of 4 cosine 2 theta. Simplify as you like. So when I put in that 0 value, I get 1 for cosine. I'm doing the square root of 4, which is 2. If I put in any of your other favorites, like I might jump ahead a little bit. Let's try pi over 2, see what happens. Because I know the cosine of 2 times pi over 2, the 2's cancel. Cosine of pi, again, is -1, -4. It gets imaginary. So I wanted to get there. There's some imaginary chunks that happen within that lemniscate also. And what's interesting is the imaginary parts can be these little, they're kind of the rest of, if you plotted them in there, they're those dotted pieces that I placed there. They can graph that if you do the imaginary plane. So jumping to pi over 2 gave me imaginary, so I'm going to back off a little bit. I'm going to try pi over 4. So I'm not going in order, but just playing. When you put in pi over 4 into theta, 2 times pi over 4 is pi over 2. Cosine of pi over 2 is 0, so we end up with 0. So what that tells me is that my first point is here, 0. When I'm facing 0, did I put that in? I put it in the wrong way, didn't I? We need to get that figured out. I put in 4. I'm going to fix that. Sorry that I jumped into that and just wrote that. We just put in 0 degrees and we walked out to 2. There. Sorry about that writing in that earlier. And when I went to pi over 4, by the time I was facing it, I'm back to 0 again. The only thing we want to confirm is we just want to make sure, I think as long as it was a nice smooth sweep that took us from there, we should put in an angle that's in between pi over 4 and 0. Of course, leaves us pi over 6. So let's just double check. 2 times pi over 6 is actually pi over 3. The cosine of pi over 3 is a half. Half of 4 is 2, so we're looking at square root of 2. That 1.41, and sure enough, it's right there. So if I circle the 3 points that I've got there on there, that is the top half of one of my lemniscate pieces. And by the way, this graph here, this when you square, what would usually, remember, look like a rose curve, that 4 cosine of 2 theta would have 4 petals of length 4. Our squared version of it, because you're square rooting, the petals go out to length of 2. Sorry, I wrote in 4 before. And they are only a pair that either face left and right or up and down. Left and right if it's cosine, up and down if it's sine. Now, that top half there, I can get the area of that. If I'm only interested in one loop, I can just take the sectors from 0 to pi over 6, 0 to pi over 4, and then I can take that times 2, and that'll give me the area of the whole thing. And so that'll be my tack on this one. So do a half, go to 0 to pi over 4, like that, and we'll square that radius, which was, interesting thing about it is we're handed r squared, so actually I'm going to forget that. I'm just going to put r squared is already handed to me, so it's 4 cosine of 2 theta. So I'm writing in r squared because that is what I was given. No need to add an additional squared in there. That's half a petal, remember? And what you want to do is take and double that, and you get the whole area of one of those. This is an important time. Rather than trying to find the angles where the rest of that lemniscate is carved out, because it does walk through all these imaginary points and then it does another leg, and it's too much. You just need to go from 0 to pi over 4, gives you the top half. That's plenty. Double it if you want one loop. You could take it times 4 if you wanted to get both loops, their area inside. It's all up to you. Last one, I'm going to get to this area inside one and outside the other. So this one and this one here, they are, if you put it into Desmos, it's kind of a nice looking picture. It's precise enough, and I think we should take advantage of that. If I do r is, got the wrong thing here, 3 sine theta, and those of you who were with me in class the other day, my computer was not graphing polar at all for no reason, and now it's working fine. So it was just some kind of funny issue that who knows what was going on with Demomo at the particular time. There we go. Boom, there it is, kind of like a little snowman. And the things that you want to notice, and I'm going to put in an angle that goes with this. The thing about these overlapping circles, we are trying to get the area inside the circle, but not inside what's called this little dimpled limicon. So it kind of looks like an egg with a little soft edge on there. So we want this upper region in here, and I wish I could shade that for you right now. I'm sure there's a way, but I'm not going to look it up. The key to doing these overlapping areas is that you create the area that you want by either adding known areas together or by subtracting areas from one another, kind of like we did in the past. If you have a big area, you can subtract out the smaller area. But for this one, I am going to, and since I've got a nice picture showing up there, I'm just going to just duplicate it real fast over on the main screen, and then we'll come back to it. So what I'm seeing is this picture. Let's flip back so I can write with you. There we go. And you need to know where they intersect. The angle that creates that intersection is important. That really looks like a snowman. If you set the two equal to each other, you can find where they intersect with one another. So we take 3 sine of theta. Those intersections are really important, just like the polar zeros are really important. Setting these radii equal to 0 will also be of importance sometimes. In this case, I think we can bypass it. Some like terms, I'm going to add sine to both sides, so I get 4 sine of theta is 2, and then you divide by 4, sine of theta is 1/2. And if you remember, these are the graph of this. We call this one, this is a circle. Daisy, S-I-R-C-L-E, spelled properly, of course, circle. And the other one is that dimpled limicon. And when I look at both of their domains, it's either 0 to pi or 0 to 2 pi. So when I think of my thetas I'm solving for, I'm going to solve for ones that are within those, either 0 to pi or 0 to 2 pi. Sine of theta is equal to 1/2 at pi over 6 is a good one. And it kind of, you can see that right here. This is definitely pi over 6. And then it can also be equal to 1/2 at 3 pi, or I'm sorry, 5 pi over 6 on the other side. Okay, so those are the other angles on there. Those are important because those are kind of like boundaries for my sweeping. The way you do area within polar is kind of sweeping boundaries like that. So as I go through this, now this is really poorly drawn, and I do need to help this out a lot the way I drew it, because you guys saw it in the picture from Domomo. There's some regions in here we need to be careful of. That circle dips below that line that I just drew in there, and there's a little region in there that we want to be cautious of. So let's flip back to the big picture so you can kind of see it. If I put in theta equals pi over 6, which I can on here, thankfully, and hit enter, I think, used to let me draw that. I guess it's not going to let me draw it, but it would usually put in a nice line through there so you could see that a little bit better. I could probably manipulate that a little bit and do it with the old rectangular, but we'll do it later. But in any case, you can see that there's going to be some area underneath that line or that vector that I would write through pi over 6, and that's not well denoted in this picture, but it's right into there. Okay, so we have some area in there. I don't want that. That's not part of it. So there's multiple ways to attack this, and in class we took on several, but the quickest route you can probably take on is if I did from pi over 6 to 5 pi over 6 within the circle, then I would get the area above that would kind of resemble this thing. It's like the top of an ice cream cone. Okay, so that's that top half there. But what happens though is that's too much area. It has some of my region that I don't want, which is that limicon stuff that it's underneath it that I need to cut out. And so for this one, we're going to do an area of the upper chunk, which is just inside the circle. So I just use that radius, and it is from pi over 6 to 5 pi over 6. These are things you usually want to test out, but for now we're just going to set it up for kind of simplicity here. And that's that circle, which is 3 sine of theta. 3 sine theta, d theta. That would be the upper part. And then in purple, of course, I'll write the other one that you want to cut out is also from pi over 6 to 5 pi over 6. Bingo. And the theta, or the radius on that one is the limicon, so you have to change that out. 2 minus sine theta squared d theta, and we're home free. That'll give you the area outside one, inside the other. You are subtracting out areas just like we always have. You know, you're taking one outside, but that's just one approach, one option for finding overlapping or combined areas. You either subtract a larger one and a smaller one to get what's left over, which is the desired upper region up there, or you can add pieces together, and that's something we'll look at in the next example, but this is enough for now. We'll give you that as a nice head start. See you all very soon. As soon as I shut this off, we're in good shape. Here it goes.